So good afternoon and welcome to this first seminar of Sustainable Nano at ICN2. So today we have the first speaker of the series is Jose Perez, who is the Health and Safety Coordinator of ICN2. But this seminar is the first of a series that we are organizing within this network, this SSN network, which let me introduce it to you. It's the Spanish network of safe and sustainable nanotechnologies. It's a network that was funded last year, and they started the activities this year for a few years. And it's based on Spanish research centers which work in the nanoscience and nanotechnology area. And the idea is to create a community that can share activities, experiences, and objectives on the field of doing nanoscience, but doing that in a safe and sustainable way. So this is the list of the institutes, of the research centers, which are forming part officially of the network, all of them based in Spain, in several cities and regions. We are here at ICN2, we are the coordinators of the network, but the idea is that this network can serve also to help and to coordinate activities of other centers which are not really members of the network. So if you are members of an institute which is not in this list, please feel free to try to participate and to contribute to the network activities. You are very much welcome. So this network was created with a mission, which is to do excellent nanoscience and nanotechnology, find new science in the nanoscale regime, and transfer this science to products and to well-being and to economic value, but to do it in such a way that we don't spoil the environment, and we do it in a sustainable and safe manner, so that the workers of the institutes, for instance, are not subject to dangers of nanoparticles or anything like that. And the idea is that the Spanish research centers lead this initiative, this task, this role, and do work on the nanoscale and are champions of sustainable and safe nanotechnologies. So we want to grow economically, to generate economic growth and value, but we want to do it in a safe manner. So the network has three main activities. One is, of course, to generate and to share all this knowledge of how to do things sustainably and safely. But then we have two very important activities, which is training to transfer these results to our personnel and to people working in nanoscience and nanotechnology in other institutions, and including also the private sector, the industry. And then communication and outreach, which is to disseminate all these results and this knowledge to the society. And this series of seminars is in these two areas, training and communication and outreach. So we have established this series of seminars, and we have already 3 seminars planned. So the first one is this one that we are having today, but there are 2 other seminars which are in the program. The first one is going to be on May the 8th by actually a member of an institute which is not member of the network, which is David Quirón from the Institute of Microelectronics in Barcelona. That's going to be in May, and he will talk about an aspect of nanoscience which is very important, which is that we are heavy users of clean room facilities, and clean rooms are especially, I would say, problematic in the sense of expense and waste of usage of electricity and water and so on. And he's going to talk about how to keep clean rooms sustainable and try to generate as less consumption and waste as possible. And then we're going to have another seminar on June the 5th in San Sebastián, who is going to talk about artificial intelligence aided synthesis and characterization of nanocrystals, of plasmonic nanocrystals. Okay, so let me go back to the presentation today. We have Jose Perez, who is again the Health and Safety Coordinator of ICN2. He has been working in the Institute for a few years now, since 2015. And he has a background actually working not in the scientific area. So he was working in something much more microscopic, in the mining business, let's say. So he was taking responsibilities of safety, health, and environment in that area. But then he moved to the pharmaceutical and chemical industry as senior consultant, and now he's working with us at ICN2 on the nanoscience area. He has a background, again, in mining engineering, but then he has a master's degree in occupational health and safety, and another master's degree in environment and quality management. And he has done a lot of activity, not only in keeping the institute safe and comply with all the requirements of the labor laws, but also to study more scientific aspects like what is the fate and the toxicity of nanoparticles which we may generate at the Institute. And I think that's what he's going to talk about today. So I leave the room for him. Jose, you are very welcome to start. And thank all of you for attending. And I hope to see you again also in future seminars of the series. Thank you very much. So Jose, you can start.
Thank you, Pablo, for this kind introduction myself. Well, I'm going to share my screen to share with you the presentation I'm going to give you today. First of all, just say that it's a proud for me and the health and safety area to start with this series of talk, introducing such a relevant topic as the health and safety handling of nanomaterials. Well, in the ICN2, the health and safety area works with the aim to integrate safety in all departments, working methods, and even in decisions. So especially on research lines, we want to foster the safety commitment in the research task. For that reason, we felt the necessity to develop further assessments in this field beyond legal requirements. On the other hand, unfortunately, regarding to handling nanomaterials, there are many uncertainties related to both the identification of potential hazards and especially the characterization of the exposure, as well as toxicological data on nanomaterials, which is still, unfortunately, largely incomplete. Well, in the next slide, I write like an overview of this presentation. I try to make a little resume that what we are going to see or what we're going to discuss. I will do a very brief presentation about our institute. Just let you know what kind of institution we are, what we do here in the ICN2. Brief slide offering you some kind of interesting numbers regarding to the ICN2. Then we move on to the research lines, what kind of research lines we develop here in our institute. We will talk about the nanomaterials chemical synthesis and nanomaterials chemical deposition, as well as one of our most important facilities, which is the nanofabrication facility. This section is very interesting just to know what kind of nano we have here. So we produce nano. We of course buy commercial nano as well to develop our research task, but we synthesize most part of them. Then I will talk about the health and safety area, which is our aim, our challenges inside the institute. And the last part will be a description of what kind of methodologies or methods to assess the exposure to nanomaterials. In this case, we will talk about the qualitative methodology, which is called control banding. It's a control banding tool, and quantitative measurements, which is one of the most, let's say, complicated part of the nanomaterials assessment, because it's very difficult to find equipment to do it. It's very unusual to have access to this equipment. Finally, I will show you two different campaigns or risk assessments that we performed in the last 2-3 years inside the institute as a practical examples of the contents that I'm talking about. Finally, I will close the presentation with some conclusions, especially in terms of corrective and preventive measures that we can take put into action in our institute to help you to take or to have some decisions if you will find in the same situation. Well, ICN2 is a non-profit international research institute located in the UAB campus in Bellaterra, which is devoted to open and explore new frontiers of knowledge at the nanoscale, mainly at the nanoscale. Thus, we try to bring this value to society in the form of new understanding in the broad fields of information and communication technologies, health, energy, and environment as well. Our expertise lie at the nanoscale, where these new properties and ways to exploit them in everyday life are being discovered day by day. And of course, we are seeking new ways to engage with local and global industry. We provide as well collaboration and expert advice, even in health and safety fields, to public and private institutions, try to fostering a responsible and transparent collaboration between researchers and the society. Then definitely this is a learning institution. That's what we are doing every day, and we do our best to inspire and providing training to next generation of researchers to deal challenges and even opportunities for the future in every fields that we have presence. This is a small slide regarding to some interesting numbers according to our activity. We have a staff of almost 300 people, including visitors, administration staff, and research staff, even interns. Nowadays, or currently, we have 19 research groups with different research lines that we will see later. Our annual budget is around 10 million euros. We have one support division, 3 units, and 6 specific facilities. We have an impact factor higher than 9 points, and we have more than 11,000 followers in LinkedIn as an example of the presence in social media. We are, Severo Ochoa Award Center. Well, in this case, since 2040, the ICN2 is awarded with this distinction, which is the highest national award conferred to a Spanish research institution. And this status has been recently renewed until 2026, enabling new research areas and thus focusing in nanosolutions in several application domains. This is one of our most important strategic plans for the future. Regarding to research lines, we have, as I told before, 19 research groups that together cover much of the breadth of nano research. The spectrum of the ICN2 research activity can be categorized in general terms, as you could see in this picture. Starting for theory and simulation research groups, nanoscale and manipulation and characterization of nanomaterials, nano device fabrication and fundamental properties of nanostructures, nano biosensing devices, and obviously chemical routes to nanostructures, which includes one of the more than 2 or 3 research groups as supramolecular nanochemistry and organic nanoparticles or energy-oriented materials. Well, if we are talking about nano, of course, as I told before, we do nano in our institution. What kind of nano we do, or what kind of nano we create? Well, there are plenty of methods to synthesize nanomaterials. And in the ICN2, these methods are grouped in 2 categories mainly, which are namely top-down and bottom-up techniques or approaches. The techniques normally are classified based on the phase of the starting material. For example, in the top-down class of techniques, the starting material is in a solid state, whereas in bottom-up techniques, the starting materials is either in gaseous state or liquid state, but normally liquid in this case. Well, top-down approach refers to a subtractive process in which a bulk starting material is divided into smaller ones of nano size in this case. For example, the mechanical grinding. In our case, there is some group that use the bulk milling of graphite, for instance. And this mechanical grinding is into extremely fine powder. So thus we could obtain, for example, graphene. Other examples are etching, which is some acid attack using strong acids, and nanolithography as well, based on depositing desired patterns with nano dimensions or dimensions of the order in nanometers on a solid material surface. In this case, this kind of top-down techniques are performed in our nanofabrication lab. Well, the bottom-up is as well performed using mainly techniques as chemical vapor deposition, metal organic chemical vapor deposition, and salt gel synthesis mainly. Well, the kind of nanoparticles we obtain mainly are inorganic nanoparticles, silica dioxide, gold, silver, platinum, cobalt, well, plenty of them. Especially, I want to highlight molybdenum disulfide, which is a tubular fibrous nanoparticle, wolfram oxide, which is obtained in rods, cadmium selenium, metal organic frameworks, and covalent organic frameworks. We obtain as well polymeric nanoparticles as polymetacrylate, polycarbonate, polyether sulfone, and polyactic acid, and carbon nanotubes. But most of carbon nanotubes, we normally buy them commercial nanomaterials. We have an important amount or significant amount of commercial nanomaterials as graphene quantum dots, titanium oxide, and several. Well, here you can see 3 wonderful pictures obtained from our microscopy unit, in where we can see metal organic frameworks in the first of them. In the second one, we can see this tubular or fibrous nanoparticles, and in the last one, we can check some polymeric nanoparticles. Well, regarding to chemical deposition, we perform graphene growth using ovens. As well, we can deposit ultra-thin nanomaterials layers using chemical vapor deposition and metal organic chemical vapor deposition. So it's both are important processes performing in our research lines day by day, which obviously have some kind of hazards regarding to the manipulation and handling, not only of the materials, but the equipment, the lab equipment as well. Well, regarding to our nanofabrication facility, as I told before, this is divided in three parts. We have one part in where we have two evaporators equipment, which are currently in a transition stage to move on into another labs, where these ultra thin layers are deposited in substrates. Then the nanofabrication facility has an etching room where we perform this strong acids attack and nanolithography space to deposit, as I told before, these patterns with nano dimensions, as you can check in this picture, just down to the 2-hour low of the ICN2 nanofabrication facility. Well, about the health and safety area and our lines of actions. Well, we try to integrate the safety in all departments, working methods, decisions, especially usually in research lines. Our aim is to foster a preventive culture in the institute. We want to increase the risk perception of safety, not only of individual safety, but in the safety of the colleagues, process and facilities, to go more beyond the legal requirements and not only complying with the current legislation. Obviously, we try to promote the participation of the ICN2 in the continuous improvement of working conditions. And one of our challenges is to make the ICN2 a reference research center, even in health and safety and its management. Don't forgetting the perspective of this continuous improvement. In the picture you can check in this slide. I put the Swiss cheese theory, in where the multi-causation theory shows that an accident is caused by the weakness in different parts of the management system. So if we do not stop this track, the accident will happen. It's very relevant for me to talk about it, because we try to be present in all of this management system, especially in the risk assessment of research line and research tasks, to avoid have these undesirable events. Well, now I'm going to talk about nanomaterials exposure assessment, what challenges we have, and what methodologies we can use to assess this exposure to nanomaterials. Well, first, I want to highlight the main challenges we have in this field. This is a field very complicated for health and safety professionals in general, because this is a fast-growing research field. As I told at the beginning of my presentation, there are many uncertainties related to identification of hazards and especially the characterization of exposure. You have to be more mature performing these assessments to accurate the hazards, and especially to accurate the features of exposure. It's well known that the toxicological data on nanomaterials is very incomplete, and it's very difficult to extrapolate the results obtained in cells or animals to humans. Normally, there are no safety data sheets or are few available. Only we can check the safety data sheets of the parent material, and normally or sometimes the nanomaterial could have different physical-chemical properties. And especially, it's very important to know that there is a lack of threshold level values in reference to airborne concentrations, and for that reason, well, we cannot perform a traditional approach of industrial hygiene, because we cannot compare a sample. If we collect samples with a pump, for example, in an environment area, in a breath environment, we cannot compare these results with level values stated by some official institutions. So we are blind in this case. Well, which is the first methodology that we can use to avoid these problems we have with this, let's say, traditional industrial hygiene approach? Well, we are talking about the control banding tool. Well, the control banding tool try to face this problem that I told before, to have this difficult to have the concrete and exposure data and chemical properties of the material. When collecting samples to know the concentration in a working environment, normally nanoparticles are not easily separated. And well, there is a discussion about what is the most appropriate index of this exposure. Maybe concentration, maybe the surface area. And in this case, the most important factor is that there are no established limits, and the toxicological data is very limited. The control banding tool is a qualitative method for risk management that groups control strategies in bands based on their level of hazard. The level that we obtain by a sum of severity factors and probability factors is stated in a matrix. These scores come from the sum of these different factors, as I told, which help us to define the hazardousness of the task, of the research task. In the case of severity score, we check different factors based mainly in physical-chemical properties, as surface chemistry of the material, particle shape, the particle diameter of the material, the solubility, and then related to the toxicology, carcinogenicity, reproductive toxicity, the mutagenicity, thermal toxicity, and asthmagen. The same for the parent material, which is the 30% of the severity score. Well, the numbers in brackets are the highest score that we can give to these factors, but this score is divided in different scores regarding to the importance of the severity factor. For example, in the case of the particle shape, if you have a nanomaterial with a circular shape, the punctuation, the score is lower than if you have an isotope form, or maybe tubular form, because it's dangerous than a circular form in terms of inhalatory tract exposure. In the case of the probability score, we obtain this number as a sum of probability factors, which normally is the point of view of the safety officer. I mean, this is normally the survey that we perform when we are assessing a task in the lab. So we usually ask for the estimated amount of material used, if the material is in powder or dust, how many employees or how many researchers are working with this exposure or performing similar tasks at the same moment, the frequency of this operation, if it's daily, weekly, monthly, and the duration of the operation. As in the severity score, the number is in the brackets, inside the brackets is the highest score, but we obtain different scores depending on the characteristics of the exposure. For example, the frequency of the operation, if you perform it daily, the score maybe will be 15 points, and if you perform this operation just weekly or monthly, maybe the score will be 7 or 5 points. And in this case, the probability score will decrease. Well, in this slide, you can see the matrix I told before, in which phase the severity and probability scores, obtaining 4 different risk levels, obviously depending on the score obtained in these factors. Well, the risk level 1 say that with general ventilation in a lab is enough to perform safely the activities. In the risk level 2, the matrix state that we need to use a fume hood or local exhaust ventilation. If we obtain a risk level 3, the task with nanomaterials must be contained, maybe in a glove box or in a specific facility. And well, in the risk level 4, the matrix say that seek a specialist advice, which is very funny, but because I don't know if we can find a higher specialist than people that normally are performing this kind of exposure assessment. So I mean, it's a very complicated, let's say, the state in where we can take some decisions or not. Well, in the case of quantitative measurements, well, we are talking about especially the nanoparticle emission assessment technique, in where we normally use some specific equipment which is not very usual to reach or to rent or even to operate, because you have to be more professional working with this kind of equipment. It's very complicated to use, and it's very difficult to find in a commercial or maybe in a health and safety environment. So we have 3 different levels for this qualitative method. In the level 1, we perform the identification of the emission sources. We try to gather information of the background level and even variations in the concentrations of the number of particles. In the level 2, we make a more important study of the type and level of particulate released, especially during the task that we want to assess. And the level 3 is repeat the level 2 measurements, but with a simultaneous collection of particles with different parameters, like mass, fiber concentration, morphology, and even chemical composition. The measurements normally are performed in the background to know which are the number of nanoparticles in our immediate environment. I mean, so the background is how many nanoparticles we have in our environment without any kind of relation with our task. So it's the background just. And in the activity process, the nanoparticles release related to our task. Normally, we make these measurements in two locations, in the near field of the activity and in the far field. We have this distance as a reference in this slide. And there you can see three pictures of the three most commonly equipment used to quantify these nanoparticles. In this case, we have a multimeter particle detector, which measures the concentrations of particles deposited on the lung surface, LDCSA. And this equipment measures as well the electrical charge of the aerosol and concentrations in terms of the diameter of nanoparticles. Then we have the nanotracer, which is a particle counter, measuring the electrical charge of particle, and the nanowatcher, which is a particle that transforms the captured particles in alcohol droplets, which are then counted by an optical detector. Well, I want to share you the experience we had performing these methodologies in our institute, trying to assess our research task. In the case of the control banding methodology, the risk assessment using control banding tool, we performed it last year, just 1 year ago, in March 2023. And this is our results. This is the control banding that we got, and where you can check that, well, most of nanomaterials or most of tasks performed are in a risk level which is paired with our facility controls. So most of them are in risk level 2, where we have obviously in all of our labs fume hoods and local exhaust ventilation beyond any other kind of measures. And I want to highlight 2 tasks that I can describe with more detail now, explaining the results of the severity factors and probability factors in where we got the risk level 3. And in this case is the cadmium selenium nanoparticle synthesis and the disulfur molybdenum nanoparticles calcination. Well, in the case of severity, the severity factors, the sum of the severity factors are in a medium level. Let's say between 50 and 75 points. Most of them, most of the nanomaterials have a spherical or compact shape, which gives a lower score in this case of the severity. The diameter, in this case, we choose the worst case scenario because during the surveys, most of researchers say that they are not sure what is the diameter or the dimensions of the nanoparticles. Regarding to the toxicology, in the case of the cadmium selenium, it's carcinogenic at macro scale. In the case of the titanium dioxide, is carcinogenic at nanoscale. So this will increase the severity factors. For example, in the case of the platinum and the disulfur molybdenum, we have these level values, the threefold level values. But whenever we have an uncertain toxicology, we always take the precautionary principle. So we give the highest punctuation to perform this control banding matrix. Now, the surface chemistry normally is a no. This is a key factor due to its reactivity. The particles mostly are insoluble. And in the case of the parent materials, well, more or less, in every cases, the toxicology and the characteristics are the same in these cases. Well, regarding to the probability and the method of synthesis, I have to say that the 90% of our research, our synthesis is performed through colloidal suspensions from a precursor and a reductant, surfactant, salt gel synthesis. It does not facilitate this release as they tend to agglomerate. Then we create substrates, polymers, films using confined reactors, chemical vapor deposition, using molecular beam epitaxy, the high vacuum chambers. Of course, we use inks containing nanoparticles, and the percentage of powder that we use always is less than the 50%. So in this case, one of the cases in what we got, the risk level 3 was in the disulfur, molybdenum disulfur, because in this case it was performed a calcination and subsequent handling of powder, and in this case the probability score it's increased. The number of people who works with the nanoparticles normally is lower than 5 people, and the frequency of exposure it's daily. Normally, the duration of the task are between 1 or 4 hours. So, assuming the severity and probability factors, this risk level 3 is obtained because of the handling powder in the case of molybdenum disulfur, and the toxicology of cadmium in the case of cadmium selenium nanoparticle synthesis. We can talk about any other exposure features performing the survey during this risk assessment campaign. There are particular tasks in the lab hazardous from our point of view, which is the spraying, spray dyeing, opening lab equipment intended normally for synthesis, as sonicator, rotary evaporator, and oven. And in these tasks, the risk could be increased. The preparation of samples for characterization normally includes handling of solutions, pipetting, or handling powder to be deposited in a substrate, normally carbon tube, to be characterized. The collaboration with companies could create a more hazardous situation than in normal terms, because of centrifugation, drying of small quantities, and especially the further handling, packaging, sieving, transport. Well, the challenges that we have, well, it's well known that we have a lack of information on communication with research groups, because normally we need to be very proactive in this case, trying to know new research lines or new nanoparticles synthesized, or maybe what kind of operations or new task they are performing, which could be increase the the probability factor in this case. The contaminated surface in the labs is not obvious. Normally, we only focus in nanomaterials, but it's well known that solvents used are of a toxic nature. For example, the dimethylformamide or dichloromethane. The use of the same fume hood for several tasks and in the same time that they are performing task handling nanomaterials. And we have the challenge of handling nanomaterials inside the fume hood it's the safer manner to work with them, but in this case we have the problem with the volatility because they are very, very light. Well, in the case of the quantitative methodology, the quantitative measurement campaign, we took the opportunity to collaborate with the NanoExplore Live project, which we investigated about potential health adverse effect caused by exposure of nanoparticles. They try to promote policies for the safe use of these materials, and in further stages, they generate a panel of recommended biomarkers to support the health surveillance of the nanoparticles exposure. Well, the scenarios chosen in this methodology are described in this picture. We choose 6 different scenarios in where we think that they could be the more representative using performing this nanomaterial synthesis. And most of them are synthesis or extraction of nanoparticles, even graphene oxide synthesis and carbon nanotube dispersions. The ICN2 participate in the second stage of this project I told before, the NanoExplore, trying to monitor and analyze particulate levels in workplaces, and not only to quantify the exposure to nanomaterials, but to take biomarker samples from people as well. We choose 2 different kind of groups for sample collection. One group with not exposed to nanomaterials, and which is called the control group, and the exposed one. We perform a follow-up during the 4 days of the study with a biological samples collection. Well, the campaign consists in these 2 types. The biological sample collections was urine collections and exhale air collection, as well as the particulate measurement according to net methodology explained before. Well, this campaign was performing in several countries at the same time: in Switzerland, Italy, Spain, France, and Germany. We took part of this study as well. The volunteers from our institute accepted to take part, and we choose among our researchers supposedly exposed to nanoparticles and other employees, the control group I told before. The biological samples, the urine or exhale air, were collected. A spirometry test were performed on these volunteers as well, and even environmental data were also gathered. by means of analyzing the composition of the environmental air. Well, as a resume of the environmental campaign, I want to show you the obtained results for the second scenario, the scenario number 2, because in this scenario we obtained the more remarkable result. Well, in this case, the graph shows the number of particles counted as a function of exposure time in a given process. So in this case, they were performing the extraction of iron oxide nanoparticles in a rotary vapor. The top graph shows the background measurements, and the bottom graph shows near field measurements, where it is drawn the LSDA, the particles deposited on the long surface. The equipment we used in this study was the same that I described before. In this case, these measures were performed by nanotracer, and the particle concentration measured by particle counters. The graph starts showing the background measurement, where we can check an intrusive process observed as a background, since the task had not yet started. It's relevant to say in this case that the scenarios chosen in the laboratory environment that characterized by not having the possibility to stop in the production or to perform a clean background measurement without any kind of process in progress. Well, after this background, the task started during the first synthesis process, these iron oxide nanoparticles inside the fume hood. But the highest concentration values were still detected in 80.67 10 to 5 grams cubic centimeter with a particle diameter of 20 nanometers. The following process consisted of the extraction of iron oxide nanoparticles using a rotary evaporator. The auxiliary tasks were the transfer, centrifugation, and sonication of iron oxide nanoparticles mixed with chloroform. During this process, as seen in the figure, no significant increase in the concentrations was detected. But at 1:20 p.m., the rotary evaporator was turned on and the sample was placed. And it was when the rotary evaporator was turned off, indicated with a red circle in the graph number 2, where the highest increase in the concentrations was detected, reaching up to 8.84 grams, 10 to 5 grams per cubic centimeter, and releasing the particles with the smallest diameter of about 10 nanometers. The rest of scenarios obtain the lower particle concentrations. In general, never more than 12,000 grams per cubic centimeter. In this case, we have 80,000. In general, in these commented scenarios, it's observed that there is a concentrations that significantly exceeds the background concentrations. So that's true that there is a concentrations in a higher concentration in the lab performing this task. So it could be a hazardous exposure to nanomaterials. Well, we think that the key factor is the use of the rotary vapor outside the fume hood. I thought it's a very short and punctual process within the usual operations in the lab. In any case, the study has facilitated the vision of a hypothetical exposure, and especially to gain knowledge to value the valuable measure, and others spending to develop as a result of the evaluation. Well, in this case, you can check further calculations that give us the result that the second scenario, the magnetic nanostructuring scenario, could be the more hazardous one. Well, as a conclusions, what about preventive and corrective measures working with nanomaterials? Well, in the ICN2 as organizative measures, we have let's say a corporative policy for working with nanomaterials, including good practices guidelines. Normally, we ask groups to communicate work with nanomaterials, its nature, the toxicity, if known. If we have safety data sheets, if we have information about the parent material. We register the commercial nanomaterials in our inventory app. So we have an exhaust list of the kind of nanomaterials we have in our institute. We suggest to planning by the PI the experiments involving nanomaterials to have a let's say an internal guideline, a lab guideline, including the laboratory equipment to be used, the characterization technique, and the state of the materials or conditions of use. If it's liquid suspension, solid, so coating state. The quantities per policy always should be less than 1 gram. The preference it's perform coatings on substrates and liquid suspensions better than handling powder. We try to include nano characteristic in procedures, especially for action against accidental release or accidental splashes. We offer researchers specific information and training on the use of nanoparticles, and even good practice, as I told in the first point. And we establish as mandatory periodically health surveillance for researchers with an intense exposure to nanomaterials, and nanoparticles, because there are specific medical protocols on this topic. Regarding to technical measures, well, the storage and transport should be performing closed and sealed containers. We use the identification label with the term nano in labs and in foods as well. The work environment in a tray with absorbent or adherent materials in laboratories with higher productions. We will try to use the hands in bag technique because it's like to have a small glove box inside your lab bench. We suggest to perform good hygienic practice, frequent hand washing, optimal group removal technique, clean work surfaces day by day with wet wipes, avoid brushing, especially if we handle powders, periodically cleaning the deposition chambers in where we normally state some work instructions to perform this task safely using HEPA filtered vacuum cleaners. We suggest always work in fume hood, glove box, biosafety cabinet, depending on the characteristic of the lab. At least we suggest to have at least one with exclusive use for nanomaterials. It's very important to mark the work area with the nanomaterials to state a control area. In the case of liquid suspensions, we suggest to work with double neutral gloves. Use preferably goggles as opposed to the classic goggles or classic safety glasses. And out of the fume hood, if you have to wait, especially powders, wear always respiratory protections with FFP3 filters. Let's say the commonly known powder mask. And finally, it's very important as well the proper management of nano waste or solutions which could include nanomaterials, marking this specific characteristic in the labels or in where our waste management supplier, as we could check, they will perform a different waste streaming after they collect the waste in our institute. Well, so that's all from my side. I'm very open to your questions, to any kind of doubts you could have about this presentation. Well, that's it. Is your turn. If we have any kind of questions or doubts, I can solve it.
Thank you, Jose, for this insightful talk. Those who have questions, you can use down below in the Q&A section where you can write your questions and Jose will answer to you. We have our first question by Marek, who says, thank you for the presentation, and can you elaborate on the aspects of proper management of nano waste? Is there any difference between management of nano waste or, for example, heavy metal-based waste?
Well, in this case, it's complicated to have an answer because normally we only mark or difference the different kind of nano waste, let's say of this nano waste, but the further processes or treatments of the waste will be performed by the external supplier, and they will have different kind of processing of this nano waste. So I can actually don't give I cannot give a specific, sorry, but I cannot give a specific answer for this question right now.
Oh, we have a question from Pilar, who also thanks you for the interesting talk. And she's wondering if it will be available a link to see later. Yes, the webinar is being recorded and it will be posted on the SustainableNano website. Okay, back to the question of Marek. He's asking if the equipment you have used to track the nanoparticles in air are commercially available.
Well, in this case, I can say that the particle counter, yes, they are commercially available, but in the case of NanoTracer, this equipment was completely enabled to perform this NanoExplore Live project. So it's a prototype. It's not a commercial one. We were very lucky to use it because it's very difficult to reach to this kind of equipment. But in the case of nanoparticle counters, the answer is yes. You can rent them, or you can ask for specific advisory officers to perform this kind of measurements.
Okay, we have another question from Pilar as well, saying that besides the data sheet, do you have information of other sources regarding normatives, advices, or protocols?
Yes, the answer is yes. We normally try to check some kind of good practices and management of nanomaterials, where we can extract some kind of information to develop our internal rules, our internal procedures. I try to check more risk assessments, any other studies in this topic, which are very, very interesting. I know that, for example, in the ceramic industry, they perform a lot of quantitative measurements because the quantities that we are talking at a higher, very higher. We are always talking about a lab scale. For example, in the case of control banding, nanotool is specific for small quantities for lab scale, but in the case of a highest exposure, like in industry, I try to check the results or the conclusions, because there is very interesting. As well, I try to read papers about studies in using some kind of bacteria, some kind of soils, well, any other materials that we can obtain toxicological or nanotoxicological data to increase the knowledge in this field, which is very uncertainly, unfortunately.
Yes, one last comment is that if inside the members of the centers that are part of the Sustainable Nano Network, if there is an interest regarding this particular topic, we can work on a group that can tackle and assess this issue.
Well, Jasmine, so I think that's all for today, right?
We can wrap up the webinar. Thank you, everybody, for your questions and also for your attendance. We hope to see you in our next seminar, which is in May.
Thank you. Goodbye. Bye.